Today we're going to look at infinite geometric series. Our objective is to be able to find the sum of a geometric series. In our last lesson we talked about the general form for S sub n, the sum of our series, and n is finite. That means it stops. So we have n equals 1 to some number. So say we're going to add the first 10 terms or 100 terms. So this would be an actual number. And this means it's a geometric, or a sub 1, r to the n minus 1. This is our rule for our geometric sequence. And if you remember, our formula was a sub 1, or again, the first term. And I'm writing a sub 1 because this says n equals 1. If this said n equals 0, this would be a sub 0. If this said n equals 5, I'd have a sub 5. Times the quantity 1 minus the common ratio to the nth power, however many numbers I'm adding together, divided by the difference of 1 minus r. So we did that before, but what happens if I change the problem and instead of stopping at a finite number, I go to infinity? That means the numbers that I'm adding together just keep going on and on and on and on. So how do we actually get a sum if we never stop adding numbers together? So let's kind of think about what happens, because the only thing that changes in this formula is this number on the top gets extremely large. So let's just make up an example. So let's say I have sigma. Let's say we'll start at n equals 1. I'm going to change this number here in a second, and let's say the rule is 4 parentheses. Let's do, say, 1/2. Just make up a number to the n minus 1. Alright, so let's pretend, again, this is n, so I'm going to keep changing my n. My formula says take the first value, so if I substitute in a 1, 1 minus 1 is 0, 1/2 to the 0 power is 1, 1 times 4 is 4. So I know my first term in the sequence is 4. 1 minus, my common ratio for this problem is 1/2. I'm going to leave the n part blank for a second, divided by 1 minus my common ratio, which is 1/2. So if you look at this formula, the only thing that's going to change if I change this from an n to an infinity is this little part right here, because that's the only place where n affects my equation. So let's just substitute in different n values and see what happens as n gets extremely large or goes towards infinity. So let's think about this. So the only part I'm going to concentrate on right now is this part right here. Okay, because this part is going to be multiplied by 4 eventually in order of operations, but we have to deal with what's inside the parentheses first. So our exponent, then parenthesis. So let's see. Let's pretend that n is, say, 10. So let's just make up a number. So say we're going to add up the first 10 terms. So this part right here would be 1 minus, in parentheses, 1/2 to the quantity, or sorry, to the exponent power of 10. So this part right here is 0.99023, and I would eventually multiply it by 4 and go on. But what if I change this and I say, well, you know what, let's not add the first 10 terms, let's add the first 100 terms together. So again, the only thing that's going to change right now is I'm going to make this 100. Oh, it says that equals 1. Okay, so what if I make the number even bigger? Let's add a few more zeros on here. Still stays 1. So 1 times anything is just itself. So this numerator, as this gets really, really big, as this goes towards infinity, this entire green part equals 1. Well, 1 times 4 is 4. So I really just get this problem, which is just a 1 on the top. Well, let's see if anything happens if I changed this number inside. So let's keep it the same, but let's pretend. Let's make this instead, I don't know, 3/5. Maybe 1/2 is too nice of a number. So let's do 1 minus the quantity 3/5. And again, I'm going to keep changing this number. So let's do 1 minus the quantity 3/5. And let's raise it to the 10th power. Alright, 0.999, not quite the same decimal. So let's make it 100. Oh, I get to 1. And if I keep making it larger and larger and larger, I go to 1. So as this number gets larger, this goes towards 1. Let's think about why that happens. What happens when I take my fraction, 3 divided by 5, and I need parentheses around that. So let's do 3/5, and let's raise it to the 10th power. Okay, so I get a tiny little decimal. Let's take the same fraction and raise it to the 100th power. I get a negative exponent, even a tinier fraction. Let's raise it to, we'll just keep putting a bunch of zeros here. Oh, now it doesn't exactly equal 0, but the calculator can't deal with such a small number, so it says it's basically 0. So what happens when you do 1 minus 0? Well, you just get 1. So that's why as our exponent gets extremely large, that means this basically goes towards 0, and 1 minus 0 is just 1, and 1 times anything is just itself. So what happens when I make this go from 1 to infinity? The only thing that changes is I don't have to worry about this parentheses. I don't have to worry about 1 minus r to the nth power, because this is going to eventually approach the number 1. Well, 1 times a sub 1 is just a sub 1. So when we are dealing with an infinite geometric series, actually our problem gets a lot easier to solve. But how can that be? How can we keep adding numbers together but get to a single value? Now, we just showed how as the exponent gets larger, our value that we're subtracting from 1 gets close to 0. But will that always happen? So let's think about a different series. So let's say n equals 1. Let's do the same thing 4, but let's make this, say, I don't know, 5/3 to the n minus 1. So let's think about this. So if I again set this up, 1 minus 5/3, 1 minus my common ratio raised to my nth power. So this is the part I'm going to change. So let's see what happens here. I'm just making up a different number. So let's do 1 minus the quantity 5 divided by 3, and let's start by raising it to the 10th power, because my last two examples worked. Oh, well, that doesn't look anything like what we did before. We get a negative 164. What happens if I raise it now to the 100th power? Oh, I get a big number, and the reason I know it's a big number is because this E22, it's a positive 22, which in scientific notation is times 10 to the 22nd power, which means I'm going to move my decimal to the right, so it's getting larger. All right, let's try it again by adding some extra zeros in here. Oh, overflow. Now, if you ever get that, that means the number is so big for the calculator, it cannot handle it. So that means this number is getting extremely large. Even with 1,000, it won't work. So 100 is the biggest number this thing can take. I mean, I could probably put like 150. But, so again, this is a huge negative number. Well, if I take a huge negative number times 4, I just get an even larger negative number. Okay? So, why did this one not work? So let's kind of analyze and think what's different between this problem and what I did before. The only thing I changed here was my common ratio. My last two common ratios were 1/2, I did a 3/5, and this one's 5/3. So this one didn't work. Okay, this did not approach 0 because this value is getting really, really big. Well, the difference is 1/2, we have 0.5, 3/5, right, is our 0.6, 5/3 is 1.667, it keeps going on. So the difference is if you keep multiplying, so let's say I start with the number 4. Okay, if I multiply by 1/2, the number is getting smaller. So that means my next number I'm adding would be smaller. Then the next number would be smaller, half as big, and then half as big. So if I keep adding numbers that are smaller, I'll eventually get to some total. But what if I started with 4 and instead I had to make it bigger? Okay, so if this number is getting bigger and bigger and bigger, well, if I keep adding more, I'm not going to get to a single value. The reason we get to a single sum is eventually I'm going to be adding, in essence, 0. So that means it stops adding new values to it. So that's what we have to be careful with. The only time that this formula works is when the common ratio, the absolute value of the common ratio, is less than 1. So don't just look for a fraction. Remember, fractions are only less than 1 if the numerator is smaller than the denominator. If you get a fraction but the numerator is larger, or you get something that's not even written as a fraction, an integer value, then we know we have no sum. So let's go through a couple of examples. The first thing I want you to do when you have these problems, we know it's geometric because we have an exponent, is look at the top. If it's infinite, okay, if there's an n value here, or 10 or 15, then you can always do the problem. But if you have to add forever, the first place you should look is your common ratio and ask yourself, is this less than 1, or the absolute value of this less than 1? And the answer is yes. Okay, r is less than 1, which means we can do the problem. So we know from before, all I need to know is the first term, and my first term is 5. and then 1 minus the common ratio of 2/3. I think you should be able to do this without a calculator, but remember 1 is 3/3. 3/3 minus 2/3 is 1/3. We don't like to divide by a fraction, so instead of 5 divided by 1/3, we're going to multiply by the reciprocal, 3/1, and then we should get our sum of 15. So if you start with the number 5, and the next sequence, the next term in the sequence is 2/3 as big, and the next one is 2/3 as big as that, the numbers are getting smaller and smaller. They'll eventually add up to 15. Let's look at our second one. Okay, it's an infinite geometric series. My common ratio is 1/2, and I know that 1/2, can do it this way too, is less than 1, so that's good. So I know I'm going to take my first term, which happens to be 100, divided by 1 minus 1/2, which is the same thing as 100 divided by 1/2, or 100 times 2/1. So we get a sum of 200. So very basic. These problems are much, much easier than what you had to do in the last section where we had a finite geometric sequence. So let's look at our last example. Again, it's infinite. I look at my common ratio. Is the absolute value of 3/2 less than 1? And the answer to that is no. Okay, because remember, this is 1.5. If I have a value 4 and I keep getting 1.5 times bigger, I'm never, ever, ever going to get a sum. So we just write no sum. Okay, it's impossible to come up to a single value. So in example 4, it says a ball falls off the edge of a shelf that is 15 feet high. If the ball bounces to a height that is 4/5 as high as the previous bounce, how far did the ball travel if it bounced 4 times and then came to a rest? So let's see why this has anything to do with what we just did. So let's pretend we have some like little shelf thing. Could draw it as an actual shelf. We have a ball, and it's going to fall off, okay, and it's going to bounce. Now, technically the ball is just going to keep bouncing straight up and down, but so we can actually see the bounces, I'm going to pretend like it bounced. It came up to about 4/5 as high as it was before. Does a second bounce, about 4/5. A third bounce. A fourth bounce. And then it's going to come to rest. And the ball is just going to sit right here. So we have bounce 1, bounce 2, bounce 3, bounce 4, and then comes to rest. So I want to know how far did the ball travel, which means, let's pretend like this was a string. If I stretched this string out and measured it, how long would it be, is basically what I'm asking. So again, what does this have to do with geometric sequences or series in that case? So we know that this ball was originally 15 feet high. Okay, which tells me if the ball falls straight down, that this part right here, okay, this little part right here, this part of the string would be 15 feet long. Okay, but now the ball bounces back up, but it bounces to a height that is 4/5 as high. So that means if I take this value and I multiply it by 4/5, I'm going to get the next height. Okay, so if you don't know how to do this, you should be able to do this one in your head and get 12, but let me just show you again. So we're going to have 15. Alright, so let's clear this out. 15 times 4/5, and you get 12. So that means that this height is 12. Okay, and then we know we're going to keep doing that. So we're going to do that 1, 2, 3, 4 times. So again, I'm going to multiply by 4/5, multiply by 4/5, and then multiply by 4/5 to get my heights. So I have 12 times 4/5, or 0.8 if you like. So I get 9.6. Multiply that by 4/5, and I get 7.68. And then multiply that by 4/5 one last time, and I get 6.144. And I don't want to round it all because then I'll get I will get an inaccurate answer. So I know that was 12, this was 9.6, this was 7.68, and this was 6.144. So I need to figure out how far the ball traveled. So you might think, well, I'll just add all these together, and that's what makes it, because we're multiplying by a common ratio, that makes it a geometric sequence, but if I add them together, that makes it a geometric series of adding it together. But if I add this up, I'm not exactly going to get how far the ball traveled, because I added 15, then I added 12, which is how far this is. But if I add 12, and I add 9.6, and I add 7.68, and I add 6.144, if I just add each one of these values once, I'm not going to get the full length of where the ball traveled, because I'm just going to get either the bounce going down or the bounce just going up. So what could I do? Well, I could double this. So let's think about this. I really want to take the sum, okay, so 15 plus 12 plus 9.6 plus 7.68 plus 6.144. Okay, so if I take all those and add it together, I get a total of 50.424. But again, that's not everything. But if I double it, now what I'm going to add is I'm going to get the second side here, the second side here, the second side here, the second side here, but oops, what it just gave me is 2 15s. But I don't want 2 15s, I want to double everything else. So what I can subtract is that first 15. So take a second to think about that. I used the geometric series, adding all these values together, but that didn't give me the actual what's happening in real life with the ball bouncing down and up. So I need to double it, but again, the ball didn't start on the ground and just magically pop up in the air. It started high and then dropped down once. So if I double that and then subtract 15, this ball then traveled 85.848 feet. That's how far this ball traveled. So what's a better way, or what could we have done instead of writing all of this out? Well, I don't need to write all of this out. What is this the same as? So this is just the sum. If I start at the first term and add, this is first, second, third, fourth, fifth. If I need 4 bounces, I actually have to add the first 5 terms, because these values represent the 4 bounces and I have my starting value. And what was my sequence? Well, I know my a sub 1, my starting was 15, my common ratio is 4/5, and I know this is n minus 1. So that's really what I'm doing. Well, I have a formula for this. A sub 1 times 1 minus the common ratio raised to the 5th power all over 1 minus my common ratio. So let me just show you that this will give us the same thing as what I just did by hand, which should have been the 50.424. So I'm going to do 15 parentheses 1 minus in parentheses 4/5 raised to the 5th power, close the parentheses, enter. I like to do just the numerator, divided by, in parentheses, 1 minus 4/5. You can put that in parentheses if you'd like. 50.424, and I could do that with only knowing where I started and my common ratio, which is 4/5. Now I know that that gives me one side of the bounce. I double it, but I know that I didn't double my original height, so I subtract 15, and that's how you can do it without writing out each of your sequences. So I could change up all numbers. I can say the ball was at 20 feet and it bounced to 2/3 as high, and you can do this. You can mimic the same exact problem over and over again. But what if I change the problem up a little bit? Okay, so what if I say how far did the ball travel if it was allowed to keep bouncing forever? So if we kind of think about what's happening here, in theory, okay, the ball would bounce, 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 bounce. And eventually we get so slow. Now we know in real life it would eventually stop bouncing, but eventually it would be bounced so small and so it'd barely be above a bounce that would basically look like it's sitting still, kind of like our infinite geometric series that we just dealt with. Because our common ratio of 4/5 is less than 1, we can do an infinite geometric series. So what I'm really doing here, the math of it, is I want to know how far the ball will bounce if I start at the first height and go on to infinity. And I know we started at 15, my common ratio is 4/5, okay, raised to the n minus 1. So this is what the problem would look like if I had done it like the other examples. But now I'm putting the twist on it about actually applying it to a ball bouncing. So let's think about it. What do we get with this? Because, if you remember, I said if it's infinite, we look at our common ratio. And since I already know it's less than 1, I know the sum is going to be the first term divided by 1 minus the common ratio, 4/5. Well, 1 minus 4/5 is 1/5. 15 divided by 1/5 is 15 times 5, which is 75. But remember, that isn't how far. All that 75 did was count each of these values once. Okay, I would keep doing all these bounces just once, but I know the ball went up and down, so I'm going to double it, which gives me 150. But if I double each of these by doing the other side, there's a problem. I doubled my original, but I don't want my original doubled, so what I'm going to do is subtract my original height, and this problem happened to be 15. So I know that if I allow the ball to keep bouncing forever, in theory, okay, it would have traveled 135 feet. And that's how we kind of deal with a ball bouncing problem with a infinite geometric series. I hope you feel a little bit better about dealing with infinite geometric series and to be able to find the sum of that geometric series.